So let's now see the first type of turbine, that is a Pelton wheel. So let's see the construction, working principle, and the diagram how it looks like, and then we'll discuss each of the parts in detail. So as you can see in the diagram, I've drawn the setup of the Pelton wheel. So it looks something like there's a dam, it stores water, and the water is directed through the penstock, and it goes on to the strikes the vanes. So there's a runner. On the runner there's vanes mounted. Sorry. So on the runner there are vanes mounted. The water strikes the vanes and it starts rotating, and eventually when it starts rotating, the rotation of the shaft goes to the generator. The generator generates electricity, and that's how the energy is converted. So as you can see, to the nozzle there's a wheel connected. So the function of the wheel is to regulate the flow of the liquid that is flowing, with the liquid, the water that is flowing. So using wheel, you can adjust the flow of the liquid that is flowing. If you want to control the discharge, if you want to control the quantity of water that is flowing, you can just rotate the wheel in a particular direction. You can do that. So next is the casing. Casing helps to prevent the splashing of water. The casing is like a cover which prevents everything from splashing. So the function of casing is only to prevent splashing, and here in Pelton wheel, everything, all the energy, all the head that the water has gets converted to kinetic energy. There's no pressure energy. So the pressure inside the casing is atmospheric pressure. So the function is to just avoid splashing of water. The water comes and strikes the vanes. The vanes start rotating. The vanes are mounted on a wheel called runner. The Also, the penstock directs water. So the net head available, as you can see, is the difference between the head at the top and the tail race. So there are losses, as we've already seen in other chapters. There are losses when the water flows through pipes. So if you eliminate the losses, if you subtract the losses from the gross head, you get net head. That is the head available for power output. So that was all about the construction in detail of the Pelton wheel. Next, we'll see the velocity diagrams and the different mathematical functions, the efficiencies, and all those stuffs of the Pelton wheel. So let's see the velocity triangle, the work done, and the efficiency of the Pelton wheel. So let's draw the bucket, that is the vane, how the vane looks like, and then we'll see the diagram, the velocity at the inlet, the velocity at the outlet, and all those things. So this is the typical diagram for the velocity diagram for Pelton wheel. Since the flow is tangential, the velocity v1, I'll name each of them. So v1 is the absolute velocity of the jet at the inlet, u is the velocity of the blade, that is the runner blade, and vr1 is the relative velocity at the inlet. So since the blade is also moving and the jet comes in, the relative velocity comes into the picture. And similarly, we have v2, u, and vr2, that is the relative velocity, absolute velocity at the outlet. Now, the inlet velocity, as you can see, it is horizontal, and the outlet velocity when the jet comes out of the bucket, it moves along a certain angle, and that angle depends on the curve of the bucket, how much the bucket is inclined. So the angle is called phi, which is the angle of deflection of the jet. So as I said earlier, the jet comes in horizontally and moves out at a certain angle. That angle is called phi, which is the angle of deflection of the jet. And generally the angle of deflection is kept between 160 and 170. So it's very difficult to maintain the angle of deflection 180 because you cannot design it is very difficult to design a bucket which makes an angle of deflection 180. And if the angle of deflection is 180, it helps us to give more momentum, and which in turn can help us to generate more power. But it's very difficult to make the angle of deflection 180, so the angle is generally kept between 160 and 170. So let's see other terms that are involved in the velocity triangles. So I've drawn the same diagram again here. Now, here in Pelton wheel, what we do is the inlet velocity is horizontal, everything is aligned, there's no triangle formed as such. You can see there's no triangle formed. The velocity v1 is the velocity, absolute velocity at the inlet, u1 is the velocity of the runner or the bucket or the vane, you can say. And there are two more velocities that you can see in this chapter. You see the components of the absolute velocity gives you these two velocities, that is the wall velocity and the flow velocity. So you can see vw2 and vf2, or you can see at the inlet side vw1. So I'll name them first of all and then explain them what they are. Now let's see what the wall velocity and the flow velocity is. Wall velocity is nothing but the horizontal component of the absolute velocity. and the flow velocity is nothing but the vertical component of the absolute velocity. As you can see at the inlet side, the velocity, absolute velocity is horizontal. So there will be no component along vertical. So absolute velocity itself is the wall velocity at the inlet. And on the outlet side, as you can see, the velocity is inclined. So since the velocity, absolute velocity V2 is inclined, it will have two components. It will have the horizontal component and the vertical component. The horizontal component of the absolute velocity at outlet gives you the wall velocity at the outlet, and the absolute velocity, the component of the absolute velocity, that is a vertical component, gives you the flow velocity. So you have V W2 and VF2, whereas on the inlet side you have VW1, and the flow velocity at inlet is 0 because the absolute velocity is horizontal, so there cannot be any flow velocity, which because it is the vertical component. So now the importance of these two velocities. The question arises, why do we take components of the absolute velocity? So the wall velocity is the velocity which helps in rotation, which gives movement to the wheels, and the flow velocity is the one which helps to give discharge. So whenever you are talking in terms of forces, whenever we talk in terms of momentum, so whenever we talk in terms of torque or the rotation, the velocity which helps to create rotation is the wall. The name itself tells wall, which means which it creates rotation. Next is the flow velocity. The flow velocity helps to give discharge. So whenever you're calculating discharge, the velocity that you'll be using is the flow. And whenever you're calculating the forces, the work done, and the torque, the velocity that you'll be using is the wall velocity. So that's their importance. And also the angle phi is the angle of deflection of the jet. So the next topic is, let's calculate the forces that are exerted on the bucket, and after we get the force, we'll move on to the work done by the force, and then we'll see the efficiency of the Pelton wheel. So the force exerted by the jet on the bucket is F is m dot VW1 plus VW2. VW1 is nothing but the wall velocity at the inlet. As I already said, the wall velocity is the velocity which helps to create rotation, which helps to create torque. So this velocity comes, the formula comes by the basic principle of Newton's second law. We have already seen impact of jets, and once you saw the impact of jet equation, you get something like this: m dot VW1 plus VW2. So m dot is the mass flow rate, which is nothing but rho a into velocity at inlet VW1. And let's see what VW1 and VW2 are. Since the velocity at the inlet is horizontal, the inlet velocity is the absolute is the velocity of the wall. So VW1 is equal to V1, whereas at the outlet side the condition is a little different. So let's draw the triangle and find VW2. So from the outlet side of the triangle, you can see the component, the horizontal component of the relative velocity gives you the total length, that is VR2 cos phi. And if you subtract VR2 cos phi with the velocity of the jet, you get the velocity of the wall at the outlet. So as I said earlier, the work component at the inlet is nothing but the absolute velocity. The work component at the outlet, we have solved it, and we have got VW2, that is the work component, as VR2 cos phi minus u. And next is the very important assumption that we have made while deriving this equation. The most important assumption here is the relative velocity at inlet is equal to the relative velocity at outlet. It's a very important assumption. We have assumed that the relative velocity at inlet is equal to the relative velocity at outlet, because we assume that the buckets are frictionless, they are shock proof, and there are no losses. So the relative velocity at inlet becomes relative velocity at the outlet. It's very important. It's an assumption made, but in practical cases there are losses, there are certain kinds of losses available, but we are making some assumptions and solving. So relative velocity at inlet is the relative velocity at outlet. The bucket is designed such that it's very smooth, it's frictionless, it's shock proof. So VR1 is VR2 which is nothing but the absolute velocity V1 minus u. So now let's substitute the value of VR2 in the equation of VW2. So we've come out with this equation of force, that is rho a v1 minus u 1 plus cos phi. This is nothing but the force that is exerted by the jet on the bucket. Now the next thing, once we've got the force, next we'll go on to the work, that is the work done by the jet per second. Now work done by the jet per second is nothing but force into the distance moved per second. Distance moved per second is nothing but the velocity. So the force times velocity will give you work done. So the work done per second, we've got the equation as rho a v1 v minus u 1 plus cos phi into u. So there's one more term called as work done per unit weight. So let's see what work done per unit weight is. So it means work done per second per unit weight of water striking. So per second per unit weight of water striking, how much work is developed. So it's something like that. So work done per second per unit weight of water striking is v minus u 1 plus cos phi into u divided by g. So we've got the force, we've got the work done per second, we've got work done per second per unit weight. Next is let's calculate the efficiency, how efficient the Pelton wheel is. So there are different types of efficiencies here. So we'll see first the hydraulic efficiency first. So hydraulic efficiency is nothing but the work done by the runner per second divided by the kinetic energy of the runner per second. And we have already calculated the work done per second, which is rho a v1 v minus u 1 plus cos phi into u. So let's substitute and see what we get. Kinetic energy of the jet is half mv square. M is rho av, so we'll get something like this: half m, which is rho a v1 and v1 square. So it comes out to, so we can cancel the terms rho a v1 So it's a very important efficiency, the hydraulic efficiency, which is nothing but the ratio of the work done by the runner per second divided by the energy input per second, and the energy input is the kinetic energy. Since we've got the efficiency, let's derive a condition in which the efficiency becomes maximum. So the next thing is we'll be deriving an equation, we'll be differentiating this equation, and we'll be calculating a term, we'll be getting an equation which will give you the condition under which the efficiency becomes maximum. So let's see what the condition is. As you can see here, the efficiency is the function of the velocity of the blade, u. So what we'll do is we'll differentiate the equation with respect to u and we'll get the condition very easily. So the next thing we'll be doing is, since the hydraulic efficiency is a function of the blade velocity, that is u, we'll differentiate it and get the condition. As you can see here, we are differentiating with respect to u, so other terms can be treated as constant. So before differentiating, I've already simplified the equation, and once the equation is simplified, you can go for differentiation. So after this step, you can differentiate the equation with respect to u. And we all know that for maximization or minimization, the derivative term, the slope has to be 0. So the next step is to put d nu by du as 0 and see what we get. So this is the condition that we got. U is v1 by 2, that is the inlet velocity. The blade velocity has to be half of the inlet velocity so as to get maximum efficiency. So we've got the condition for maximum efficiency, right? So u, that is the velocity of the bucket or the velocity of the runner, has to be half of the inlet velocity of the jet at the inlet. So half of the velocity of the jet at the inlet. So we've got the condition for maximum efficiency. So if you substitute this condition in the equation of efficiency, you will get the maximum efficiency, the formula for maximum efficiency. And after substituting, you get something like this. So this is the formula for maximum hydraulic efficiency, and the condition is the velocity of the bucket or the vane has to be half of the inlet velocity of the jet. So and the maximum hydraulic efficiency is 1 plus cos phi by 2. So this is the maximum hydraulic efficiency. So let's now move on to the next topic, that is different types of efficiency in the Pelton wheel. As you can see here, I've shown two different a block diagram, kind of a block diagram, which will help you understand the types of efficiencies. So initially what we have is the water power, the power that the water contains, which is the potential that it has. And though the potential is converted into kinetic energy and it is given to the runner, and the runner develops its own work, and that work is given to a shaft, and the shaft gives up the power output. So the first efficiency is the hydraulic efficiency, which is the runner output divided by the water power input. So hydraulic efficiency is the work done by the runner per second divided by the water power, that is the kinetic energy the water has. And we've already derived the equation, we have derived the condition for maximum efficiency, and we've already seen what the maximum efficiency is. And next is, after the runner does the work is given to a shaft. And now the shaft gets the work and it goes to the generator and develops power. So next thing is the mechanical efficiency, which is the power that is developed by the shaft, and it's the ratio of the power that is developed by the shaft and the runner, the work done by the runner. So mechanical efficiency is the power output, the net power output divided by the work done by runner per second, and if you multiply these two terms you get overall efficiency. So these three are the types of efficiencies that we have in Pelton wheel: the hydraulic efficiency, the mechanical efficiency, and the overall efficiency. So hydraulic efficiency is nothing but the work done by the runner per second divided by the kinetic energy of the jet per second. Mechanical efficiency is nothing but the power output by the shaft divided by the runner, the work done by the runner. And overall efficiency is nothing but the product of the hydraulic efficiency and the mechanical efficiency. So the product of both will give you the overall efficiency, which is nothing but power output divided by the kinetic energy input. So that was all about the theory part of this Pelton wheel. Let's now move on to the numericals of the Pelton wheel. Thank you.